Okay, so we're going to go through and start doing some Newton's second law examples because ultimately the way you get better with physics is you do practice problems. So in this problem, we have two masses, mass 1 and mass 2, which we know they're over here. They are touching each other, and there's a force, which we know, pushing against it, along a surface that has a coefficient of friction, and we want to find the acceleration. So you might imagine that the acceleration is probably going to point this way, right? Our block is going to accelerate in the x direction to the right. So what I'm going to do, first I'm going to draw a coordinate system, and I'm just going to put it, generally speaking, right here in the middle. This is our y, this is our x, okay? So our block represents our origin, is kind of how we're thinking of it. It might also be helpful to think of this as just a point, which we'll do with our free body diagram right now. But real quick, I want to make a note that we're looking for the acceleration of not just block 1 and not just block 2, but both. Because the blocks are together, they're going to accelerate at the same acceleration. So we're going to look at this as a system, which is mass 1 plus mass 2. So whenever they're together, you can think of this as just being one thing. That's why I drew the coordinate axis just right there in the middle. That is our system. So if we were to draw a free body diagram, this dot represents the two masses together. Now, if we think of our non-contact forces, the weight force, which is mass times gravity, and the mass of our system is just mass 1 plus mass 2 times g. So because we're thinking of these masses together, the mass of everything is just the two masses added together. And that'll spit out a normal force. We have, I'm just calling it force F, this little push force. We're also going to have a force due to friction. Now, because I'm saying it's going to accelerate, my prediction at least is that it's going to accelerate toward the right, this red vector needs to be bigger than this blue vector because the red vector is going to give us our net acceleration. Okay? And if not, then we can adjust that accordingly. But now we can do Newton's second law. If you ever do a free body diagram, the whole point of that is to make Newton's second law a little bit easier. So I'm going to start. We can see we have forces acting in the y direction, like this, and forces acting in the x direction, like this. So we can look at forces in the x or y direction. I'm going to start by looking at x motion, just because that's where we're saying it's going to accelerate, which is ultimately what we want to know. So we just start writing Newton's second law. The sum of all forces in the x direction is the mass of the system, which is m1 plus m2, times our x acceleration. What forces are acting in the x direction? Well, we have that force of the push, which is in the right, so that's positive, minus the force of friction, and that should be equal to m1 plus m2 times our acceleration in the x direction. Or, if we divide both sides by m1 plus m2, we'll have our force minus our force of friction over mass 1 plus mass 2 is equal to our acceleration. So we isolated acceleration, that's great. The problem is, what's the force of friction? We don't know the force of friction. But what we do know, something to know, and I'll put this just right here. The force of friction is equal to our normal force times our coefficient of friction. In our last video, that was one of the equations I gave you. So we can substitute this with our force minus our normal force times our coefficient of friction over m1 plus m2 equals our acceleration. So we know this, we know our coefficient, we know both masses. What we don't know is their normal. But we know normal's happening in the y direction, so it's worthwhile to do our y motion too. So the sum of all forces in the y direction is equal to mass times acceleration in the y direction. Now, the block's just moving in the x direction. This block isn't bouncing up and down on the floor, right? So there's no acceleration in the y direction. What forces do we have? Normal minus the weight force is equal to 0. Or normal equals the weight force, which we mentioned is m1 plus m2 times g. So now we can represent normal in terms of things we do know, which is our mass and gravity. So that could just be substituted in, boom, boom. And the force of friction here, that was substituted in from there. So our force minus G mu naught K times m1 plus m2, all divided by m1 plus m2 is equal to the acceleration in the x direction, which is our acceleration. And all you have to do is plug in the numbers. We know everything. And once you plug in the numbers, you should get an acceleration of about 1.95 meters per second squared. So that means both blocks, mass 1 and mass 2, have the same acceleration. So acceleration 1 equals acceleration 2, which turns out to be 1.95 meters per second squared. So because they have the same acceleration, we knew they would have the same acceleration, we can think of this as a system, which I haven't talked about this yet, but this is one thing to consider. You could try thinking of this as you could look at the forces on mass 1, you could look at the forces of mass 2, but it's going to get kind of weird because they're going to have a normal force. So yeah, M1 will have a force pushing on it, which will have a normal force, and then there's a normal force on the mass 2. You could do that, and you could find the acceleration of both blocks, but whenever they're in contact together like this, and you know they'll be moving at the same speed, it's helpful to think of it as a system, which you represent as just one point. So that's something to always consider if you're working through a problem. And then from there, we did our free body diagram, which was the whole reason we talked about all the different forces was because I wanted you to be able to draw this. Without this, the problem's hard. And then also to expose you to things like this, which I haven't shown you yet. Then from there, use Newton's second law, which we've talked about, F equals ma. And we worked through them. We worked through the x direction first, just because that's where that's what we're ultimately looking for, is x acceleration. We replaced the force of friction with that equation I gave you. And then we looked in the y motion to find the normal. Substituted that in, and then just plug in the numbers. And that's all there is to it.